Right now as you read this, the universe is on fire. Not metaphorically, not poetically, literally. At this exact moment across the observable universe alone, a sphere roughly 93 billion light-years in diameter, approximately 1 trillion stars are actively burning. 1 trillion nuclear furnaces, each one converting millions of tons of hydrogen into helium every single second, releasing energy so vast that human language has never developed adequate words for it. The sun, your sun, the star that warms every living thing you have ever known, converts 600 million tons of hydrogen into helium every second. It has been doing this for 4.6 billion years, and by the standards of the universe, it is an utterly unremarkable mid-sized middle-aged star of no particular distinction. 1 trillion stars, burning, right now. But here is what most people never stop to consider. That number, staggering as it is, represents a phase, a season, a window of time that will not last forever, and that measured against the full lifespan of the universe has barely begun. The era you were born into, the era in which stars exist at all, is not the default state of the cosmos. It is an exception, a brief, radiant anomaly sandwiched between an unlit beginning and an unlit end that will stretch so far into the future that the word forever collapses under the weight of it. The universe will die, not today, not in any time frame that registers against human experience or the lifespan of civilizations or even the lifespan of species, but it will die. The stars will go out one by one over timescales, so incomprehensible that the entire current age of the universe, 13.8 billion years, every supernova, every galaxy, every ocean, every heartbeat will amount to less than a single breath compared to what comes after. The darkness that follows will last so long that the word darkness itself becomes inadequate. There are no words for what follows. What you are about to understand will permanently alter how you see the night sky. If you find yourself drawn to journeys that take you to the very edges of what is knowable, to the places where science and philosophy dissolve into something larger, then do something small for this channel. Hit the like button. Subscribe. It takes a moment, and it genuinely helps this work reach others who need it. Let the breath slow. The last light is already counting down. Let's begin. To understand where the universe is going, you first need to understand where it is. And where it is right now is extraordinary in a way that is almost impossible to appreciate from the inside. Cosmologists, the scientists who study the universe as a single object, its birth, its structure, its fate, have developed a framework for thinking about cosmic time that divides the entire lifespan of the universe into distinct eras. Not eras in the way historians use the word measured in centuries or millennia, eras measured in powers of 10, orders of magnitude. Timescales so large that they require a different kind of mathematics just to write them down cleanly. The era you inhabit has a name. It is called the Stelliferous Era, from the Latin stella, meaning star, the era of stars. It began approximately 100 million years after the Big Bang, when the first stars ignited in the darkness of the young universe, and it will end somewhere around 100 trillion years from now, written as 10 to the power of 14 years, when the last star burns out. 100 trillion years. To put that number in any kind of human context, consider that the entirety of recorded human history spans roughly 5,000 years. The age of the universe itself is 13.8 billion years. The Stelliferous Era will last approximately 10,000 times longer than the universe has already existed, and we are standing near its beginning. That is where you are. Not in the middle of cosmic time, not in the twilight. You are in the early morning of the only era in which light exists. The physicist and cosmologist Fred Adams at the University of Michigan, along with his colleague Greg Laughlin, spent years developing what they called the 5 ages of the universe, a rigorous, scientifically grounded framework for mapping the full timeline of cosmic history from the Big Bang to the last possible moments of existence. Their work, published in the late 1990s and expanded since, remains one of the most sobering and beautiful pieces of scientific literature ever produced. They wrote not as doomsayers, but as astronomers who simply followed the physics wherever it led, and the physics led somewhere very cold, very dark, and very final. But not yet. Right now, the universe is doing something it will never do again in quite this way. It is making stars. The process by which stars are born has not changed since the first ones ignited 13.7 billion years ago. Gravity gathers clouds of gas, primarily hydrogen, the simplest and most abundant element in the universe, and compresses them until the pressure and temperature at the center become sufficient to initiate nuclear fusion. At that point, hydrogen nuclei begin fusing into helium, releasing energy in the form of light and heat. The star ignites. It pushes back against its own gravity with the force of that released energy, and a balance is struck, a dynamic equilibrium between the inward pull of gravity and the outward pressure of nuclear fire. That balance is a star. That balance is the sun. Stars come in an extraordinary range of sizes, temperatures, and lifespans. The most massive stars, the giants, the supergiants, burn through their hydrogen with such ferocious intensity that they exhaust their fuel in only a few million years. They are the brilliant, profligate members of the stellar family, luminous beyond comprehension but brief. When they die violently, in explosions called supernovae that briefly outshine entire galaxies containing hundreds of billions of other stars. They seed the universe with heavy elements, carbon, oxygen, iron, all the atoms that eventually find their way into planets, into oceans, into the cells of living things. In a very literal sense, every atom in your body, heavier than hydrogen, was forged in the core of a star that no longer exists, flung outward by its death. At the other end of the scale are the small stars, the dim ones, the red dwarfs. A red dwarf is a star so modest, so restrained in its burning, that at first glance it barely seems to qualify. The smallest red dwarfs are about 1/10 the mass of the Sun, and they burn so slowly, so carefully, that they will continue fusing hydrogen for not billions but trillions of years. Some of them will still be burning long after the Sun has died, long after the solar system no longer exists, long after the Milky Way has changed beyond recognition. The smallest red dwarfs alive today will still be alive, still producing light, still maintaining their quiet nuclear fires in 100 trillion years. They are the last stars. They are the embers that will burn longest before the Stelliferous Era finally ends. Right now, red dwarfs make up approximately 70 to 75% of all stars in the Milky Way. They are everywhere, though almost none are visible to the naked eye from Earth. They simply do not produce enough light. Proxima Centauri, the closest star to the Sun, is a red dwarf. It sits just 4.24 light-years away, and yet it cannot be seen without a telescope. It burns at roughly 30000 degrees Kelvin on its surface, compared to the Sun's 5500 degrees. It is a whisper, where the Sun is a shout, and it will still be whispering long after the Sun is ash. To feel the scale of the Stelliferous Era, properly consider this. If you compress the entire future lifespan of the universe, from now until the very last events that physics permits into a single calendar year, then the present moment, including the entire history of human civilization, the entire age of the Earth, even the entire 13.8 billion year history of the universe so far, would fall somewhere in the first few seconds of January 1st. The era of stars would end sometime around late January. Everything that follows, the incomprehensible epochs of darkness, the slow decay of matter, the evaporation of black holes, the long dying of everything, would fill the remaining 11.5 months of that year, all of it occurring in absolute, total, permanent darkness. We live in those first seconds of January, and the fire is extraordinary. There is a concept in astronomy called the cosmic star formation rate, a measure of how rapidly the universe is generating new stars at any given time. When astronomers look backward through time by observing distant galaxies, they find that the universe reached its peak rate of star formation approximately 10 billion years ago, in a period cosmologists sometimes call cosmic noon. At that time, galaxies were forming new stars at a rate perhaps 10 to 30 times higher than they do today. The universe was younger, denser, its gas, clouds richer and more abundant. Stars were being born everywhere in enormous numbers, with a frequency that the present-day universe cannot match. Since then, the rate has been declining. The Milky Way today forms perhaps 1 to 3 new stars per year, Some galaxies form more, many form far less. The raw material, the cold hydrogen gas that gravity needs to make new stars, is being consumed. Stars fuse it into heavier elements and lock it away in stellar remnants, or they disperse it through stellar winds and supernova explosions. The universe is not creating new hydrogen. The inventory that existed after the Big Bang is the inventory it has always had, and that inventory is slowly being spent. Star formation will not simply stop one day. It will taper. It will thin. New stars will continue to form for trillions of years, but they will be increasingly smaller, increasingly dimmer, increasingly the red dwarfs that burn so slowly they are nearly invisible. The brilliant massive stars, the ones that produce the blue-white light that gives galaxies their luminous arms, are already dying out. They have lifespans of millions of years, and the ones being formed today will exhaust themselves long before the Stelliferous Era ends. What will remain as the era draws toward its conclusion, 100 trillion years from now, is a universe lit only by the faintest of red embers, billions upon billions of ancient red dwarfs spread across the cold darkness of intergalactic space, each one burning alone. And even that will end. But before we reach that ending, it is worth pausing inside this moment, this cosmically improbable, radiant, temporary moment, to understand what it actually means that we exist here. Life, so far as we know, is possible only because energy flows. Because there is a differential, a hot thing and a cold thing, and energy moves from one to the other, and in that movement complexity can arise. Stars are the source of that differential in our corner of the universe. The sun pours energy onto the Earth, and the Earth radiates that energy back into the cold of space, and in the gap between those two temperatures, in that narrow thermodynamic window, chemistry becomes biology. Molecules become cells. Cells become organisms. Organisms become conscious. Remove the stars, and you remove the energy differential. Remove the energy differential, and you remove the conditions for life. This means that everything you know, every person, every ecosystem, every civilization, every thought that has ever been formed into language exists because we happen to inhabit the one slim era in the universe's history when nuclear fires are burning in the sky. The warmth is not a background condition, it is an event, a finite event. The universe is 13.8 billion years old. The Stelliferous Era will last approximately 100 trillion years, which means that by the universe's own reckoning we are roughly 0.014% of the way through the age of stars. The fire has barely caught, the candles are still being lit, and yet even here, in the deep early morning of the stellar age, the physics that will eventually extinguish everything is already at work, written into the nature of stars themselves, patient, precise, and absolute. Every star is burning down its own fuel supply. Every star is a countdown. And the universe contains no mechanism for making more hydrogen. No process by which the raw material of stars can be replenished once it is spent. The inventory is fixed. The furnaces are lit. And one by one, over timescales that dwarf the imagination, they will go out. The first to go are already gone. The massive blue giants that burned briefly and brilliantly in the early universe have long since exploded and faded. The sun itself, an ordinary yellow dwarf, more massive and shorter-lived than the red dwarfs, but far less extreme than the giants, has approximately 5 billion years remaining before it exhausts its hydrogen and swells into a red giant, engulfing the inner planets. That event is not coming soon by any human measure, but it is coming. And when the sun goes, it will take with it every ocean, every continent, every trace of whatever life existed here. The Earth will be absorbed. The light that sustained 4 billion years of biology on this planet will become the instrument of its destruction. Yet even that will not be the end of the Stelliferous Era. The sun is a brief chapter. The red dwarfs will outlast it by a factor of thousands. They will burn on dim and patient for another 100 trillion years, the last lights in a universe that is slowly surrendering its warmth to the dark. To stand under a night sky and look up at the stars is to look at fire that is already dying, not quickly, not visibly, but irrevocably. Each point of light is a nuclear reaction borrowing time against an inevitable exhaustion. The universe made a finite amount of fuel, ignited it in the first stars, and has been burning through it ever since. The brightness of the present sky, that scattered brilliance that humans have navigated and mythologized and written poetry about for the entirety of their existence, is the product of that burning. It is beautiful. It is temporary. It is the universe at its warmest. What comes after is something that the human mind evolved to think in spans of years and generations is profoundly ill-equipped to comprehend. The darkness that follows the Stelliferous Era does not last for millions of years or billions or even trillions. It lasts for spans of time so vast that the Stelliferous Era itself, 100 trillion years of burning stars, will eventually seem by comparison to have been a flash, a spark, a single breath in a silence that stretches toward forever. But the darkness comes in stages, and the next stage begins not with darkness but with the slow and patient dying of suns. The sun will not explode. That is the first thing to understand. The dramatic deaths, the ones that briefly outshine galaxies, that scatter heavy elements across light years of space, that compress matter into objects so dense a teaspoon would weigh 1 billion tons. Those deaths belong to the massive stars, the giants, the blue supergiants that burn with such ferocious intensity that they exhaust their hydrogen in a few million years and then collapse under their own gravity in a catastrophic implosion. Those stars die loudly, violently, with a brilliance that can be seen across the observable universe. The sun will die quietly. In approximately 5 billion years, when the hydrogen in the sun's core is finally exhausted, the nuclear reactions that have maintained the balance between gravity and pressure will begin to falter. The core will contract under gravity, heating up as it does. That extra heat will cause the outer layers of the sun to expand slowly at first, then dramatically. Over the course of hundreds of millions of years, the sun will swell into what astronomers call a red giant. Its surface will cool and redden as it expands, but its total luminosity will increase enormously. At its maximum extent, the sun will be large enough to engulf Mercury, Venus, and almost certainly the Earth. The oceans will have boiled away long before that moment. The atmosphere will have been stripped. Whatever exists on the surface of this planet in 5 billion years, if anything does, will be consumed. But even that is not the end of the sun. It is only the beginning of its dying. After the red giant phase, the sun will shed its outer layers in a slow, expanding shell of gas called a planetary nebula. The name is misleading. It has nothing to do with planets. Early astronomers simply thought the glowing shells looked vaguely planet-like through their telescopes. What remains after the outer layers are expelled is the core, a dense, hot remnant, roughly the size of the Earth, but containing more than half the sun's original mass. This object is called a white dwarf, and it is here in the concept of the white dwarf that the story of stellar death becomes something much stranger and much longer than most people ever consider. A white dwarf does not burn, it does not fuse atoms, it produces no new energy of its own. What it does is glow, radiating the heat accumulated over its entire lifetime as a star gradually cooling over time. Think of it as a coal pulled from a fire. The coal is not burning, but it is still hot, still radiating warmth, still slowly losing its stored energy to the surrounding air. A white dwarf does the same thing, but on a timescale that makes the human mind real. The sun's white dwarf remnant will begin its cooling process at a temperature of perhaps 1,000,000 degrees Kelvin. It will cool, slowly, very slowly. The rate of cooling depends on the white dwarf's mass composition and surface area, but in general the process takes an extraordinarily long time. Current models suggest that for a white dwarf to cool to the temperature of the cosmic microwave background, the faint residual warmth left over from the Big Bang, currently sitting at about 2.7 Kelvin, just barely above absolute zero, would take longer than the current age of the universe many times over. Some estimates place it at more than 2 quadrillion years, 2 followed by 15 zeros. In fact, astronomers believe that no white dwarf in the universe has yet had time to cool completely. The universe is not old enough. Every white dwarf that has ever formed is still warm, still glowing, however faintly. The universe has not yet produced what theorists call a black dwarf, a completely cooled, dark, inert white dwarf remnant. Not a single one exists yet anywhere in the observable universe. They will exist eventually, in enormous numbers, but not yet. This single fact carries within it a kind of quiet astonishment. The universe, 13.8 billion years old, has not yet had time to completely cool even one dead star. When the Stelliferous Era finally ends, when the last red dwarf burns out 100 trillion years from now, the universe will be filled with the cooling remnants of every star that has ever lived. White dwarfs beyond counting each one, slowly releasing its stored heat into the surrounding dark, each one on a cooling curve that stretches for quadrillions of years. The sky will not go instantly dark when the last star dies. It will dim gradually, over timescales so vast they would require new notation just to write them down. But before we reach that cooling darkness, there are other kinds of death to understand. The massive stars, the ones many times heavier than the Sun, do not leave white dwarfs behind. When a massive star exhausts its nuclear fuel, it does not gently shed its outer layers. It collapses. The outer layers fall inward at a significant fraction of the speed of light, crashing into the increasingly dense core with catastrophic force. The resulting explosion, a core collapse supernova, releases more energy in a few seconds than the Sun will emit over its entire 10 billion year lifetime. The shock wave tears the star apart, and what is left behind, if the original star was massive enough, is one of two things. If the collapsing core has a mass between roughly 1.4 and 3 times the mass of the Sun, the result is a neutron star. A neutron star is an object of almost incomprehensible density. It packs more mass than the Sun into a sphere roughly 20 kilometers across, about the size of a city. The density is so extreme that the electrons and protons that normally make up atoms are crushed together into neutrons, giving the object its name. A sugar cube-sized piece of neutron star material would weigh approximately 1 billion tons on Earth. The surface gravity is roughly 200 billion times stronger than Earth's. If you were somehow transported to the surface of a neutron star and fell from a height of 1 meter, you would impact the surface at approximately 7 million kilometers per hour. Neutron stars are also extraordinarily fast. When the core of a massive star collapses, conservation of angular momentum, the same principle that makes a spinning skater speed up when they pull in their arms, compresses whatever rotation the original star had into a vastly small object. The result is a neutron star that can spin hundreds of times per second. Some neutron stars, called millisecond pulsars, rotate more than 700 times per second, faster than a kitchen blender. These objects are so regular in their rotation that astronomers use them as natural clocks, timing signals accurate to better than 1 part in a trillion. The most precise timekeepers in the universe are the remnants of dead stars. Some neutron stars emit narrow beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep across space like the beam of a lighthouse. If the Earth happens to lie in the path of one of those sweeping beams, we detect a regular pulse of radio waves, sometimes X-rays, sometimes visible light, arriving with clockwork precision. These are pulsars, and their discovery in 1967 by the then graduate student Jocelyn Bell Burnell at Cambridge University was so unexpected, so unlike anything astronomers had anticipated, that the first detected signal was briefly labeled LGM1, Little Green Men. Bell Burnell and her supervisor Anthony Hewish had not found extraterrestrial intelligence. They had found a dead star spinning 30 times per second. If the collapsing core is more massive, still more than roughly 3 times the mass of the Sun, then not even the neutron pressure can resist gravity's final demand. The core continues to collapse past the neutron star stage, past any known form of matter that can withstand the pressure, and it becomes a stellar mass black hole. The collapse does not stop. There is nothing left to stop it. And around that collapsed core, a boundary forms the event horizon inside, which gravity is so strong that not even light can escape. These are the endings available to massive stars. Supernova, then, neutron star or black hole, brilliant in death, leaving behind the most extreme objects in the known universe. But here is the quiet, overlooked truth that bears repeating. The massive stars are already mostly gone. The universe formed most of its massive stars early in those first few billion years, when gas was abundant and star formation was running at its peak. Those stars burned quickly and died quickly. The stellar landscape of the present universe is dominated by smaller, dimmer, longer-lived stars. The era of the great supernova explosions, the era that seeded the universe with heavy elements that produced the neutron stars and black holes, is gradually winding down. There are still massive stars forming, still supernovae occurring. The Milky Way probably experiences a supernova somewhere in its volume once every 50 to 100 years. But the rate is declining, and it will continue to decline as the available gas is consumed. What replaces the drama of the massive stars is the patience of the small ones. Red dwarfs, those dim, cool, almost invisible stars that make up the majority of all stellar objects, will outlast everything else by an enormous margin. A red dwarf with half the mass of the Sun can burn hydrogen for roughly 50 billion years. A red dwarf with 1/10 the mass of the Sun, barely large enough to sustain fusion at all, can burn for perhaps 2 to 10 trillion years. Some models suggest that the very smallest red dwarfs, sitting at the lower limit of what counts as a star, could burn for up to 12 trillion years. The Sun, for comparison, will be dead in approximately 10 billion years total. The smallest red dwarfs will outlive the Sun by a factor of more than 1,000, and there is something else about red dwarfs that makes them the last survivors of the Stelliferous Era. Unlike larger stars, which develop a radiative zone that prevents their outer hydrogen from reaching the core, many red dwarfs are fully convective. The hydrogen in their outer layers is constantly circulated down into the burning core, meaning they can eventually consume nearly all of their available fuel, not just the hydrogen in the core, but the hydrogen throughout the entire star. A fully convective red dwarf is like a campfire that can reach out and pull in fuel from the entire surrounding forest. It burns more completely, more efficiently, and therefore for far longer. Imagine the last trillion years of the Stelliferous Era. The universe at that point would be almost unrecognizable. The Milky Way as we know it, with its elegant spiral arms, its blue-white massive stars, its nebulae glowing with the light of stellar nurseries, will be gone. Those structures depend on ongoing star formation and short-lived massive stars for their appearance. Without them, the galaxy will be a dim, diffuse collection of aging red dwarfs, white dwarf, remnants, neutron stars, and black holes spread across a much wider, more dispersed distribution than the tight spiral we inhabit now. The galactic center will still contain its supermassive black hole, but the luminous structure around it will have faded. The remaining red dwarfs, now ancient, perhaps several trillion years old, will be slowly cooling even as they continue to fuse hydrogen. They will have changed composition over their long lives, becoming richer in helium as fusion converts hydrogen. Some models suggest that very old, fully convective red dwarfs may briefly swell slightly before settling into a final phase of cooling, becoming what are called blue dwarfs, hotter and bluer, as the hydrogen runs out and fusion conditions change slightly. No blue dwarf has ever been observed because the universe is not old enough to have produced one. They are theoretical objects predicted by physics, but not yet existing anywhere. The universe has not given us time to see them yet. Eventually, even the last red dwarf will exhaust its hydrogen. It will swell briefly and then settle. Its outer layers will not form a dramatic planetary nebula the way the Sun's will. The process for very low-mass stars is quieter, less energetic. The remnant will be a white dwarf, dim cooling, no longer generating any energy of its own. And when the last red dwarf's nuclear fire finally goes out somewhere around 100 trillion years from now, the Stelliferous Era will be over. No new stars will form. The gas that once fed star formation will have been locked away in stellar remnants or dispersed too thinly across intergalactic space to be gathered by gravity into new clouds. The universe will still contain light, the fading thermal glow of countless white dwarfs, each one on its own long cooling curve. But there will be no new light, no new fusion, no new fires lit in the dark. The universe will have used up its stars. What follows has a name. Cosmologists call it the Degenerate Era, the age of degenerate matter squeezed into states so dense that quantum mechanics rather than thermal pressure holds it up. White dwarfs, neutron stars, and black holes, the remnants of everything that burned, they will inherit a universe that is growing darker and colder by the quadrillion year, drifting through space in a silence so complete It makes the present silence of the void seem warm by comparison. The white dwarfs will cool. It will take an almost incomprehensible amount of time, but physics is patient. 100 trillion years ago, if you can extend your imagination that far back though, of course, there was no back in that direction, yet the universe had not yet formed its first stars. The darkness was simple. There was no light because fusion had not yet begun. The darkness of the Degenerate Era will be different. It will be a darkness filled with the cooling corpses of everything that ever burned, ghost stars, dead but still present, each one carrying the residual warmth of a fire that has been out for longer than the age of the present universe. To stand in that darkness, if standing were possible, if a planet could survive around a cooling white dwarf, if some form of life or awareness could persist, that long would be to stand in a graveyard so vast that the light from the nearest dead star would take years to reach you, and even then would be too dim to cast a shadow. The universe would be quiet. The nuclear fires that have burned since the first stars ignited would be silent. No new explosions, no new nebulae, no spectral lines glowing in the infrared from distant star-forming regions. Just the long, cold, patient cooling of what remains. But the Degenerate Era holds more than cooling white dwarfs. It holds a surprise. A process so slow that it makes the cooling of white dwarfs seem rushed. A decay so fundamental that if it occurs, it will not merely end stars, it will end matter itself. And it may already be happening. 1505. Claude responded, "There is a number that may be the most important number in the future history of the universe, and almost no one knows it. There is a number that may be the most important number in the future history of the universe, and almost no one knows it. It is written like this: 10 to the power of 34. That is a 1 followed by 34 zeros. In years, it is the approximate lower bound on the half-life of the proton, the minimum amount of time that must pass, according to certain theoretical models, before there is a 50% chance that any given proton in the universe will simply cease to exist. Not decay into something heavier, not split apart into smaller pieces through some nuclear reaction, simply vanish. Transforming into lighter particles, a positron perhaps, and a neutral pion that itself decays almost instantly into gamma rays and then gone. The proton, which you have probably thought of as a permanent and fundamental constituent of matter, may not be permanent at all. It may have a lifespan, a very long lifespan, far longer than anything we have yet measured, but a lifespan nonetheless. This is not fringe physics. It is not speculation in the pejorative sense. Proton decay is a prediction of grand unified theories, the class of theoretical frameworks that attempt to unite 3 of the 4 fundamental forces of nature into a single coherent description. Most serious attempts to build a theory that unifies electromagnetism, the strong nuclear force, and the weak nuclear force predict that protons must eventually decay. The question is not whether but when, and the answer, depending on the specific theory, ranges from approximately 10 to the power of 34 years to perhaps 10 to the power of 40 years or beyond. To confirm proton decay, experimentally physicists have built enormous detectors, deep underground, shielded from cosmic rays and background radiation. The most famous of these is the Supermassive detector in Japan, a cylindrical tank containing 5,000,000 metric tons of ultra-pure water, surrounded by more than 11,000 photomultiplier tubes capable of detecting the faint flashes of light that would be produced if a proton inside that water decayed. Supermassive has been watching, patiently, for decades. It has not yet detected a single confirmed proton decay event. This does not mean protons are immortal. It means that if protons do decay, they do so less frequently than the detector's sensitivity can currently measure. The non-detection has pushed the lower bound on the proton lifetime higher and higher, ruling out some theoretical models and constraining others. The search continues. Larger detectors are planned. Hypermassive, a successor to Supermassive with a volume roughly 10 times larger, is currently under construction. The experiment is one of the most profound in the history of science, an attempt to watch matter itself come undone. But even if proton decay occurs on the longer end of the predicted timescales, say 10 to the power of 40 years, its consequences for the universe are absolute. Because if protons decay, then everything made of protons eventually decays. And everything made of matter is made of protons. Every white dwarf, every neutron star, every planet that has survived the death of its parent star, every asteroid drifting through cold interstellar space, every atom that was once part of a living thing scattered by stellar winds across galaxies, every molecule of water locked in ice around a dead star, all of it, every piece of ordinary matter in the universe would eventually dissolve, not quickly, not all at once, but one proton at a time. Over timescales that make the Stelliferous Era look like an afternoon matter itself would simply stop existing. The Degenerate Era, that long twilight of cooling white dwarfs and silent neutron stars, would come to an end, not through any dramatic event, but through the patient statistical inevitability of decay. The white dwarfs would thin and fade, not just from cooling but from losing their very substance. The neutron stars, already exotic and extreme, would lose their protons and transform slowly into something else, a sea of leptons and radiation diffusing outward into the expanding void. The planets, the asteroids, the molecular clouds too thin to form new stars, all of it dissolving into the simplest possible particles which themselves would eventually annihilate or decay further. If this is how matter ends, and we do not yet know with certainty that it is, then the universe will not merely go dark, it will go empty. But that emptiness is still an almost incomprehensible distance away. To understand what the universe will look like long before proton decay completes its work, we need to look at what happens to the large-scale structure of the cosmos during the Degenerate Era, the slow unraveling of galaxies, ejection of stars into intergalactic space, and the inexorable consolidation of mass into the objects that will ultimately dominate the universe long after every star has died. Those objects are black holes. To understand how black holes come to dominate you, first need to understand what happens to galaxies when their stars die. A galaxy is not a static structure. It is a dynamic system constantly evolving through gravitational interactions between its members. Stars pass close to one another, exchanging gravitational energy in what physicists call two-body relaxation. In most of these encounters, the effects are subtle, a slight deflection of one orbit here, a minor transfer of energy there, but over very long timescales these encounters accumulate. The statistical effect of countless small gravitational nudges, operating over trillions of years, is to gradually rearrange the orbits of stars within a galaxy. The result of this process, operating over timescales of roughly 10 to the power of 19 to 10 to the power of 20 years, a billion times longer than the current age of the universe, is that galaxies evaporate. Not through any violent event, but through a slow, statistical sorting. When two stars interact gravitationally, one tends to gain energy and the other tends to lose it. The one that gains energy moves into a wider orbit, farther from the galactic center. The one that loses energy sinks inward. Over many such encounters, some stars gain enough energy to reach escape velocity to be flung entirely out of the galaxy into intergalactic space. These ejected stars drift away into the void alone, cold, traveling in straight lines through the dark for essentially forever. The stars that lose energy in these encounters sink toward the center. There, the supermassive black hole waits. At the center of the Milky Way sits Sagittarius A times a black hole approximately 4 million times the mass of the Sun. At the centers of most large galaxies, there are similarly massive objects, some far larger, some slightly smaller, but all of them accumulating mass over cosmic time through the accretion of gas, the capture of stars, and the merging of smaller black holes. During the Stelliferous Era, these supermassive black holes are dramatic objects surrounded by glowing accretion disks, sometimes powering jets of particles that stretch across millions of light-years, blazing as quasars visible across the entire observable universe. But quasars require fuel, they require gas and matter actively falling in. As galaxies age and their gas supplies are exhausted, the accretion slows, the quasars quiet. The supermassive black holes at galactic centers become dormant, sitting in darkness at the hearts of aging galaxies no longer actively consuming, simply waiting. And in the Degenerate Era, after the last stars have gone out, those waiting black holes will begin to receive the stars that gravitational interactions have been slowly funneling toward them for trillions of years. Not in a dramatic flood, not quickly, but steadily over timescales measured in powers of 10 that grow larger with each passing epoch. The degenerate remnants, the white dwarfs and neutron stars and cooling stellar corpses will spiral inward and be consumed. Picture what this looks like, insofar as anything looks like. Anything in an era without light. The universe is dark. The white dwarfs that once glowed faintly with residual heat have been cooling for quadrillions of years. The dimmest of them are approaching the temperature of the cosmic background, which is itself cooling as the universe expands, dropping toward absolute zero on a timeline of its own. The neutron stars are dark. The black holes are dark. There are no nebulae, no molecular clouds, nothing glowing with the energy of star formation. The sky, if a sky can be said to exist when there is no planet to observe it, from no atmosphere to scatter light, is not merely dark. It is dark in a way that has no analogue in any human experience. The cosmic microwave background, that faint afterglow of the Big Bang that currently fills all of space at a temperature of 2.7 Kelvin, will have redshifted further as the universe expands. By the time the last stars have been dead for a few quadrillion years, the background temperature will have dropped to something like 10 to the power of -10 Kelvin, a temperature so close to absolute zero that the difference between it and true zero is essentially unmeasurable. Space itself will be, for all practical purposes, at absolute zero. The cold will not be the cold of a winter night, or the cold of interplanetary space, or even the cold of deep intergalactic space as it exists today. It will be a cold so fundamental that it approaches the theoretical lower limit of temperature itself. In that cold and dark, the supermassive black holes will grow. By approximately 10 to the power of 20 years, that is 100 quintillion years from now, the galactic evaporation process will be essentially complete. Most of the stellar remnants that once made up galaxies will have been either ejected into intergalactic space or consumed by the central black hole. What remains of each galaxy will be a single, enormously massive black hole, perhaps billions or even trillions of times the mass of the Sun, sitting alone in the center of an enormous gravitational well, surrounded by a diffuse halo of isolated stellar remnants too far away to be easily captured, and a vast surrounding emptiness in which individual black dwarfs and neutron stars drift in silence. These supermassive black holes will be the dominant objects in the universe, not because they are active, not because they are consuming matter at any appreciable rate, but simply because they are the most massive coherent structures remaining. They will sit in the dark, each one the gravitational anchor of what was once a galaxy, now containing most of that galaxy's mass compressed into a singularity. Around them nothing glows, nothing burns, nothing moves on any timescale that would register against geological time, let alone human time. And here is the thing about the universe at 10 to the power of 20 years. It is not in any way hostile or dramatic. It is simply quiet, profoundly, absolutely, permanently quiet. The violence that characterized the early universe, the supernovae, the gamma ray, bursts, the collisions of galaxies, the quasars blazing across billions of light years, all of that is over. Has been over for longer than the current age of the universe, many times over. The universe at this point is not dying in any active sense. It has already died. What remains is aftermath. The physics that operates at this point is still the same physics. Gravity still works. The remaining particles still obey quantum mechanics and thermodynamics. The universe is not broken or strange. It is simply empty and cold and dark in a way that admits no exceptions. Every region of space that has been mapped, every direction in which we might look, would reveal nothing. No stars, no galaxies, no light. Nothing but the faint residual traces of things that burned out quadrillions of years ago, cooling in the dark. Yet even this is not stillness. Even here things are happening, just very, very slowly. The isolated black dwarfs and neutron stars ejected from their galaxies are drifting outward through intergalactic space on straight-line trajectories carried by the momentum imparted when they were flung out. The universe's expansion continues, slowly increasing the distances between everything. On timescales of 10 to the power of 25 to 10 to the power of 30 years, there is a small but non-zero probability that two of these isolated stellar remnants will pass close enough to one another to interact gravitationally to capture each other into a binary system, spiraling slowly inward as they radiate gravitational waves and eventually merging. These mergers will be the last collisions in the universe, brief flickers of gravitational wave emission in an otherwise silent cosmos, detectable in principle, but with nothing left to detect them. And somewhere in there, if proton decay occurs on the shorter end of the predicted timescale, around 10 to the power of 34 to 10 to the power of 40 years, matter itself begins to come apart. The black dwarfs, those cooled remnants of stars, will not merely cool into inert darkness, they will dissolve. Proton by proton, the dense degenerate matter of each stellar remnant will transform into radiation and leptons diffusing outward. The process is slow enough that a given black dwarf will not visibly change on any timescale shorter than the proton lifetime itself. But across the vast spread of time that constitutes the Degenerate Era, every piece of ordinary matter in the universe will eventually participate in this dissolution. The neutron stars too will eventually succumb, though the physics of their decay is more complex, involving neutrons as well as protons, and the calculations are correspondingly uncertain. But the endpoint is the same. Whatever timescale the specific decay rate turns out to imply, there is a point at which every compact object made of ordinary matter has dissolved. Every planet, every asteroid, every white dwarf, every frozen remnant of a world that once had oceans, gone. Not destroyed in any violent event, simply transformed through the inexorable statistics of quantum decay into radiation and the lightest possible particles. By somewhere around 10 to the power of 40 years, if proton decay proceeds on the predicted schedule, the Degenerate Era is over. The universe contains no ordinary matter in any significant quantity. The stellar remnants are gone. The black dwarfs are gone. The neutron stars are gone. What remains? Black holes. Only black holes. The supermassive ones at the centers of what were once galaxies, and the smaller stellar mass black holes scattered through the intergalactic void. These are the only objects that survive the dissolution of matter, because they are not made of protons. They are made of space-time. They are not matter compressed. They are a region of space in which gravity has become absolute, in which the geometry of space-time has curved past the point of return. Proton decay cannot touch them because there are no protons in them to decay. They are beyond the reach of matter's mortality. And so the universe enters what cosmologists call the black hole era, the age in which the only structures of any significance are black holes drifting through a dark and nearly empty cosmos, slowly separating from one another as the universe continues to expand. No light, no warmth, no matter, just the silent spinning remnants of galactic centers holding within their event horizons the compressed memory of everything that once existed. These black holes will not simply sit unchanged forever. They have their own mortality, their own countdown, and it was discovered by a physicist who was not looking for it sitting in a garden in Cambridge in the early 1970s, who suddenly realized that black holes objects, so defined by their impermeability, their absoluteness, their utter refusal to let anything escape, were leaking. Wu Lingzhou. Claude responded, Stephen Hawking was 31 years old when he made the discovery that would define his scientific legacy, and he did not want to believe it at first. Stephen Hawking was 31 years old when he made the discovery that would define his scientific legacy, and he did not want to believe it at first. It was 1974. Hawking was already widely regarded as one of the most brilliant theoretical physicists of his generation, despite, or perhaps because of the physical constraints imposed by the motor neuron disease that had been progressing since his early 20s. He had been working on the quantum mechanical properties of black holes, attempting to understand what happens when you apply the rules of quantum field theory, the framework that governs the behavior of particles at the smallest scales, to the extreme gravitational environment near a black hole's event, horizon. The calculation was difficult, the mathematics demanding, and the result when it emerged was deeply unwelcome. Black holes radiate, not because anything escapes from inside them. The event horizon is absolute nothing that crosses it can return, and that statement holds for every known physical process. But Hawking's calculation showed that something subtle and strange happens at the event horizon itself, in the quantum vacuum of empty space just outside it. And understanding that process requires first understanding something peculiar about the nature of emptiness. Empty space is not empty. This is one of the most counterintuitive and thoroughly confirmed results of quantum field theory. The vacuum of space, the lowest energy state of any quantum field, is not a featureless void. It seethes with activity. Virtual particles flicker into existence in pairs, a particle and its antiparticle borrowing energy from the vacuum for an instant so brief that it falls within the limits set by Heisenberg's uncertainty principle, and then annihilating back into nothing before any measurement can confirm they existed. Under normal conditions, this process is invisible and has no net effect on anything. The particle pairs appear and vanish without leaving any lasting trace. But near the event horizon of a black hole, the situation changes. The intense gravitational gradient at the horizon means that space itself is curved and warped in ways that affect the behavior of these virtual particle pairs. In Hawking's calculation, what emerges is this: occasionally a virtual particle pair forms very close to the event horizon, and before the two particles can annihilate each other, one of them crosses the horizon and falls inward. The other, suddenly separated from its partner and unable to complete the annihilation, becomes real. It escapes. It travels outward into space as genuine thermal radiation. From a distance, it looks as though the black hole is emitting particles, as though it is warm. The energy for this radiation has to come from somewhere, and it comes from the black hole itself. By the conservation of energy, when a particle escapes carrying positive energy, the infalling partner carries negative energy into the black hole, reducing its total mass energy by an infinitesimal amount. The black hole loses mass. Slowly. Extraordinarily slowly. But it loses it. This is Hawking radiation, and its implications are extraordinary. The rate at which a black hole radiates depends on its temperature, and the temperature of a black hole, as defined by Hawking, is inversely proportional to its mass. A small black hole is hotter than a large one. A stellar mass black hole, perhaps 10 times the mass of the Sun, has a Hawking temperature of approximately 6 billionths of a Kelvin. That is 0.000000006 degrees above absolute zero. The radiation it emits is so faint, so cold, so sparse that it is utterly undetectable by any instrument that currently exists or is likely to exist in the near future. The power output is measured in units, so small that the decimal point would be followed by dozens of zeros before you reached any significant digit. For a supermassive black hole, the kind that sits at the center of a galaxy containing billions of solar masses, the temperature is even lower, billions of times lower than the already infinitesimal temperature of a stellar mass black hole. The Hawking radiation from such an object is so vanishingly faint that it makes the stellar mass case look intense by comparison. These objects are for all practical purposes in the present universe completely dark. The cosmic microwave background radiation at 2.7 Kelvin is far hotter than the Hawking temperature of any known black hole. Black holes in the present universe are actually absorbing more energy from the background radiation than they radiate away through the Hawking process. But the universe is cooling. The background radiation is being stretched and diluted by cosmic expansion. Eventually, in the very deep future of the black hole era, the background temperature will drop below the Hawking temperature of even the largest black holes. At that point, the balance tips. The black holes will radiate more than they absorb. They will begin irrevocably to lose mass. The evaporation process is self-accelerating. As a black hole loses mass, its temperature rises because the Hawking temperature is inversely proportional to mass. A hotter black hole radiates more intensely. More radiation means faster mass loss. Faster mass loss means higher temperature. Higher temperature means even faster radiation. The process accelerates as the black hole shrinks slowly at first, then faster, then faster, still until in the final moments, the last remnant of mass is radiated away in a brief intense burst of high-energy gamma rays. For a stellar mass black hole of 10 solar masses, the complete evaporation time works out to approximately 2 times 10 to the power of 74 years, 2 followed by 74 zeros, a number so large that it dwarfs the timescales we have discussed so far, the way the age of the universe dwarfs the lifespan of a mayfly. For the supermassive black holes at galactic centers, the ones containing billions or even trillions of solar masses accumulated over the entire Stelliferous Era, the evaporation time is longer still. A black hole of 1 billion solar masses would take approximately 2 times 10 to the power of 96 years to evaporate completely. The largest black holes conceivably produced by cosmic evolution, those that have grown through billions of years of galactic mergers and gas accretion, might take up to 10 to the power of 100 years, a Google years. The number that gave Google its name, chosen precisely because it represents something at the outer edge of comprehensibility. A Google years. To appreciate the depth of that number, consider the following. The entire history of the universe from the Big Bang to the present is approximately 1.38 times 10 to the power of 10 years. The end of the Stelliferous Era, 10 to the power of 14 years, is 100,000 times longer than that. The complete dissolution of matter through proton decay, 10 to the power of 40 years, is 10 billion trillion times longer than the Stelliferous Era, and the evaporation of the largest black holes, 10 to the power of 100 years, is so many orders of magnitude beyond the proton decay timescale that placing the two on the same number line would make proton decay's timescale invisible. The black holes will sit in the dark, cooling infinitesimally slowly, radiating particles so cold and sparse that no detector could ever register them for a duration that makes every other timescale in the universe's history seem like a rounding error. And during all of that time, what is the universe doing? Expanding, cooling, emptying. The cosmic expansion continues throughout the black hole era, stretching the distances between the isolated black holes ever wider. By the time the smaller stellar mass black holes have evaporated somewhere around 10 to the power of 74 years, the universe is so expanded that even if any two black holes existed within what was once a single galaxy's volume, the distance between them would be so vast that light from one could not reach the other in any reasonable time. The universe is not merely dark, it is becoming geometrically isolated. Each black hole exists in its own increasingly separated region of space-time, a lone point of extreme curvature in an otherwise featureless, flat, cold, expanding void. The Hawking radiation these black holes emit, the only energy output of any kind in this era, is so cold that it falls far below any wavelength we can meaningfully describe in familiar terms. The photons and particles emitted have energies so low wavelength, so long, that they stretch across distances larger than the observable universe was at the present moment. To call this radiation dim would be to misuse the word. It is radiation in the most technical sense, only a sparse, frigid trickle of particles separated by distances that make intergalactic space seem crowded. Yet for all the emptiness, for all the cold, for all the almost absolute silence of the black hole era, something is still happening. Physics has not stopped. The laws that governed the formation of the first stars still govern the evaporation of the last black holes. The same equations that describe the nuclear fusion in a star's core describe in their quantum mechanical extensions the particle pair production near an event horizon. The universe is not broken. It is not violated. It is simply very, very old. There is a strange beauty in this, if you can hold it in your mind without flinching. The black holes that dominate the black hole era are in a very real sense the final repositories of information about everything that ever existed. Every star that burned, every planet that formed, every galaxy that spiraled through the cosmos for billions of years. All of that history, all of that structure and complexity was eventually absorbed either by the direct consumption of matter or by the dissolution of matter through proton decay, followed by the absorption of the resulting radiation. The black holes ate everything, or more precisely, they ate what was left after everything else had already dissolved. And now, through Hawking radiation, they are giving it back. This brings us to one of the deepest unsolved problems in theoretical physics, known as the black hole information paradox. When matter falls into a black hole, the information about that matter, its quantum state, the precise arrangement of its particles, all the details that distinguished it from any other configuration of matter, appears to be destroyed. The black hole simply adds the infalling mass to its total and adjusts its three external properties, mass, charge, and spin. Everything else, every detail, seems to be gone. This violates a fundamental principle of quantum mechanics, which states that information can never truly be destroyed, only transformed and scrambled, but always recoverable in principle. Hawking's original calculation suggested that the radiation emitted by an evaporating black hole is purely thermal, essentially random, carrying no information about what fell in. If this is correct, then, when the black hole finally evaporates completely, all that information is gone forever, and quantum mechanics is violated at a fundamental level. This troubled physicists enormously, and it troubled Hawking himself deeply enough that he spent decades wrestling with it. The current theoretical consensus, driven largely by developments in string theory and the study of quantum gravity, is that information is not destroyed, that it is somehow encoded in the Hawking radiation emitted over the black hole's entire lifetime, scrambled beyond any practical recovery, but preserved in principle. How this encoding works, exactly how quantum gravity manages to preserve information, while general relativity insists nothing can escape, remains one of the most active and contentious areas of theoretical physics today. The answer, when it is found, will likely require a complete theory of quantum gravity, a framework that does not yet exist in finished form. But for the purposes of the universe's future, the resolution of the paradox matters less than the endpoint. Whether the Hawking radiation carries information or not, the black hole evaporates. The process concludes, and when the last black hole, the most massive, supermassive remnant of the largest galaxy cluster that ever existed, finally completes its evaporation somewhere around 10 to the power of 100 years, the final burst of radiation dissipates into space, and then nothing. Not nothing in the way that word is used casually. Not nothing as in quiet or empty or dark. Nothing in the most literal physical sense. No black holes. No ordinary matter dissolved quadrillions of years ago by proton decay. No radiation of any significance. The Hawking photons long since redshifted by cosmic expansion into wavelengths so long they have no meaningful energy. No structures of any kind. No gradients of temperature or density around which complexity could form. Nothing but an expanding, cooling, featureless void, carrying within it perhaps a sparse population of electrons and positrons, the lightest stable charged particles, which have no known decay mechanism, drifting apart at velocities imparted by the last particle interactions, quadrillions of years prior, separated by distances so enormous that the probability of any two of them ever encountering each other again approaches zero. This is the dark era, the era that follows the black hole era, the endpoint toward which all of thermodynamics, all of cosmic evolution, all of the physics that has operated since the first moment has been pointing. Maximum entropy, thermal equilibrium, the heat death of the universe. The concept of heat death does not mean the universe becomes hot. It means the opposite. It means that all temperature gradients, all differences between hot things and cold things have been eliminated. It means that energy is distributed as evenly as possible across the entire volume of space, with no concentrations, no pockets of order, no regions where work can be extracted from the flow of energy. In thermodynamic terms, entropy, the measure of disorder, the measure of how evenly energy is distributed, has reached its maximum possible value. In a universe at maximum entropy, nothing can happen. Not in the sense of nothing being permitted, in the sense of nothing having any energy differential to drive it. A process requires a source and a sink, a hot side and a cold side, a high energy state and a low energy state. When all differences are eliminated, when the universe is the same everywhere and in every direction, at the same unimaginably low temperature, there is no driving force for any process whatsoever. The universe does not explode at this point. It does not announce its arrival at heat death with any event. It simply becomes the final state, the background against which nothing further occurs. The universe in the dark era is not dying. It has already died by every meaningful definition of that word. What remains is aftermath stretched across an expanse of space and time so vast that the word eternal is not an exaggeration. Yet even here, in the absolute darkness of the dark era, quantum mechanics insists that something is still true. The laws of physics have not been repealed. Electrons and positrons still obey the equations that describe their behavior. The geometry of space-time still follows Einstein's field equations modified by whatever quantum corrections ultimately prove correct. The uncertainty principle still holds. Virtual fluctuations still occur in the quantum vacuum, vanishing before they can leave any lasting trace. And there is a theorem, a mathematical result from classical mechanics that has survived into modern physics in modified form that whispers something extraordinary into the silence of the dark era. Something that suggests the story may not be quite as finished as the heat death scenario implies. That theorem has a name, and the timescale it introduces makes even the Google years of black hole evaporation look like a brief prologue. 1511. Claude responded, Henri Poincaré was not thinking about the end of the universe when he proved his recurrence theorem in 1890. Henri Poincaré was not thinking about the end of the universe when he proved his recurrence theorem in 1890. He was thinking about a much smaller problem. He was trying to understand the long-term behavior of dynamical systems, mathematical systems, that evolve over time, according to fixed rules like the orbits of planets or the motion of gas molecules in a container. The specific question he was examining was whether such systems left to evolve for long enough would eventually return to states close to their starting configurations. His proof showed that they would. Given enough time, a bounded dynamical system with conserved energy will return arbitrarily close to any previous state not once but infinitely many times. The system might wander far from its starting point. It might explore an enormous range of configurations, but eventually, inevitably, the laws governing it will steer it back. This result, the Poincaré recurrence theorem, is mathematically rigorous. It applies without exception to any system that meets its conditions. The question for the universe is whether those conditions are met. The theorem requires that the system be bounded, that it occupy a finite volume of phase space, the abstract mathematical space that describes all possible configurations of the system. It requires that the system's energy be conserved, and it requires that the laws governing the system be time reversible at the fundamental level which quantum mechanics generally is. If these conditions hold for the universe, then the recurrence theorem applies. Given enough time measured not in googles but in numbers that make googles look like rounding errors, the universe would spontaneously fluctuate back into states resembling its current configuration. The timescale for a Poincaré recurrence of the entire observable universe, a fluctuation large enough to reproduce something resembling the current arrangement of matter and energy, is approximately 10 to the power of 10 to the power of 120 years. This number is not merely large. It is large in a way that requires a moment of genuine stillness to absorb. It is 10 raised to a power that is itself 10 raised to the power of 120. The number of zeros you would need to write it out in full would exceed the number of atoms in the observable universe by an incomprehensible margin. There is no metaphor that does it justice. There is no analogy that scales. The number simply sits there at the outer edge of what mathematics can write and physics can contemplate, representing a duration so vast that every other timescale discussed in this entire journey, the Stelliferous Era, the Degenerate Era, the Black Hole Era, the heat death itself is contained within it as an infinitesimal fraction. And at that timescale, the recurrence theorem says the universe could fluctuate back. Not certainly, not by design, but by the same logic that says a shuffled deck of cards, shuffled enough times, will eventually return to its original order. The universe, given enough time, might spontaneously assemble itself back into something resembling what it looks like now. Stars, galaxies, planets, the particular arrangement of atoms and fields that currently constitutes the observable cosmos. Not because anything directed it, not because any law required it, simply because in the infinite patience of quantum fluctuations, even the most improbable configurations eventually occur. This is not a comforting thought in the way it might first appear to be, because the same logic that allows a full recurrence of the universe also allows something far stranger, far more unsettling, and far more probable. It allows a Boltzmann brain. The concept originates with the 19th century Austrian physicist Ludwig Boltzmann, who spent much of his career wrestling with the thermodynamic arrow of time, the question of why the universe evolved from a low entropy beginning toward the high entropy present rather than the other way around. Boltzmann proposed that even in a universe at thermal equilibrium, statistical fluctuations would occasionally produce temporary pockets of low entropy, structures spontaneously assembling themselves from the random thermal motion of particles. He suggested that our entire observable universe might be one such fluctuation, a momentary improbability in a vastly larger cosmos at equilibrium. His contemporaries found this deeply troubling, and subsequent analysis has revealed why. The problem is one of probability. Any given fluctuation is exponentially more likely to be small than large. A fluctuation large enough to produce a single atom is vastly more probable than a fluctuation large enough to produce a molecule. A fluctuation large enough to produce a molecule is vastly more probable than one large enough to produce a protein, and a fluctuation large enough to produce a functioning brain, a self-aware observer, is almost unimaginably more probable than a fluctuation large enough to produce that brain, together with a consistent physical external universe, extending billions of light years in every direction. This means that in the Dark Era, during the incomprehensible timescales of the Poincaré recurrence epoch, the most common form of observer to spontaneously fluctuate into existence from the quantum vacuum would not be a human being embedded in a rich physical universe with a consistent past. It would be a disembodied brain, a momentary self-contained structure of matter, complex enough to be briefly conscious, surrounded by nothing flickering into existence for an instant, with false memories of a universe that never happened, and then dissolving back into the void before any external verification could be made. These are Boltzmann brains. They are a genuine prediction of the physics of eternal fluctuation, and they are philosophically catastrophic, because if they are more probable than you are, then by standard probabilistic reasoning, you are more likely to be one than to be a genuine observer embedded in a physical universe. The fact that your experience seems consistent, that your memories seem reliable, that the universe seems to extend beyond your immediate perception in coherent and testable ways. None of that provides certainty that you are not a Boltzmann brain, because a Boltzmann brain would have exactly those experiences constructed from random fluctuations rather than genuine history. Most cosmologists find this conclusion unacceptable, not merely uncomfortable but unacceptable in a scientific sense, a sign that something in the theoretical framework that generates it must be wrong. If a cosmological model predicts that Boltzmann brains should be vastly more numerous than ordinary observers, most physicists take that as evidence against the model rather than evidence that we are Boltzmann brains. The search for a cosmological framework that naturally avoids the Boltzmann brain problem is one of the motivating forces behind various theories of eternal inflation and multiverse cosmology, which brings us to a very different kind of answer to the question of what happens after the last black hole evaporates. The eternal inflation framework developed by Alan Guth at MIT and extended by Andrei Linde, Alexander Vilenkin, and others proposes that the inflationary expansion that drove the universe's explosive growth in its first fraction of a second never truly stopped. It stopped in our region, the region that became the observable universe, but inflation is a self-reproducing process. In an inflating universe, quantum fluctuations constantly nucleate new regions of inflationary expansion, each one branching off into its own expanding bubble universe, with its own physical constants, its own laws, its own history. Our universe is one bubble among an infinite number, each one evolving independently, most of them bearing no resemblance to ours. In this framework, the heat death of our universe is not the end of everything. It is the end of our particular bubble. Somewhere not in any direction, we could point to not in any spatial relation to our own cosmos, but in the larger inflating background space. Other bubbles have already formed and will continue to form for what the mathematics suggest is a genuinely infinite duration. The multiverse does not die. Individual universes within it come to their thermodynamic conclusions, but the larger structure continues its self-reproduction indefinitely. This is not a proven theory. The multiverse is one of the most contentious concepts in contemporary physics, precisely because its predictions about other bubbles are by the construction of the framework almost certainly untestable from within our own. We cannot observe other bubble universes. We cannot send signals to them or receive signals from them. The evidence for eternal inflation is indirect, inferred from the properties of the cosmic microwave background and the theoretical elegance of the framework, not from any direct detection of other universes. Many physicists are deeply skeptical of theories whose central claims lie beyond any conceivable experimental test. Others argue that untestability does not imply incorrectness, and that the mathematical self-consistency and explanatory power of eternal inflation warrant taking it seriously. A related but distinct possibility is the Big Bounce. In certain models of quantum gravity, particularly loop quantum cosmology, developed by Abhay Ashtekar and his collaborators at Penn State, the singularity at the beginning of the Big Bang is not a true singularity. Quantum gravitational effects prevent the density from reaching infinity. Instead, the collapsing matter of a previous universe, having reached the maximum density that quantum gravity permits, bounces the contraction, reverses into expansion, and a new Big Bang emerges from the ruins of the old cosmos. In the Big Bounce scenario, our universe did not begin from nothing. It began from the compressed remnant of a previous universe, and when our universe eventually reaches its final state, whether through heat death or some other endpoint, the processes of quantum gravity may eventually generate a new bounce, new expansion, a new Big Bang. The universe becomes cyclical, not in a simple periodic way, not repeating itself exactly, but cycling through phases of expansion and contraction, or some analog thereof each phase, producing new structure, new physics, new history. The Big Bounce, like the multiverse, is not confirmed. Loop quantum cosmology is a serious and mathematically sophisticated research program, but it remains incomplete. It does not yet offer a full, consistent theory of quantum gravity that makes all the predictions of general relativity in appropriate limits, while also resolving singularities. The bounce scenario is a prediction of models, not yet of a finished theory. And whether a bouncing universe would carry any information from its previous incarnation, whether there would be any continuity between one cycle and the next, is a question that current physics cannot definitively answer. There is also the question of dark energy, and whether its current behavior is truly constant. The accelerating expansion of the universe, first measured in 1998 by Saul Perlmutter, Brian Schmidt, and Adam Rees, in observations of distant Type Ia supernovae work for which they were awarded the Nobel Prize in 2011, attributed to dark energy, a component of the universe whose nature remains almost entirely mysterious. The simplest model is a cosmological constant, a fixed energy density of empty space that remains constant as the universe expands and drives ever faster acceleration. In this model, the future is the heat death scenario we have been tracing. But there are other possibilities. Some models of dark energy allow its density to change over time. In a class of models called phantom dark energy, the energy density actually increases as the universe expands, leading to a dramatically different end state. In these models, the accelerating expansion does not simply continue as it currently does. It accelerates faster and faster, the rate of expansion increasing without bound, until eventually the expansion is so rapid that it overcomes not just the gravity holding galaxy clusters together, not just the gravity holding individual galaxies together, not just the gravity holding solar systems together, but eventually the electromagnetic forces holding atoms together, and then the nuclear forces holding atomic nuclei together, and finally even the quantum mechanical structure of space-time itself. This scenario is called the Big Rip. In a Big Rip universe, the end does not come through patient cooling and decay over googles of years. It comes on a specific date, perhaps 20 billion years from now. perhaps more, depending on the dark energy model when the expansion tears everything apart simultaneously. Clusters, galaxies, solar systems, planets, molecules, atoms, and finally the fabric of space itself all ripped apart in the same moment. The universe does not fade to dark, it shreds. Current observations do not favor the phantom dark energy models. The data, as best as we can currently measure it, is most consistent with a cosmological constant dark energy that stays constant rather than increasing. But the measurements are not yet precise enough to conclusively rule out phantom models, and the question of dark energy's ultimate nature is one of the most important open problems in cosmology. Future missions, including the Euclid Space Telescope launched in 2023 and the Nancy Grace Roman Space Telescope planned for the late 2020s, are designed in part to constrain dark energy models with much greater precision than is currently possible. What all of these possibilities share: the heat, death, the Poincaré recurrence, the multiverse, the big bounce, the big rip, is that they are honest. They are what the physics says followed wherever it leads without softening the conclusions to make them more comfortable. And the honest conclusion is that we do not know with certainty how the universe ends. We know the physics of stellar death with considerable confidence. We know the thermodynamics of the Degenerate Era. We know the mathematics of Hawking radiation. But at the very edge of the timeline, at the scales of Poincaré recurrences and quantum gravity and dark energy's ultimate behavior, we are working at the frontier of human knowledge, where the equations give answers, but the answers raise deeper questions than they resolve. There is something appropriate about that. The universe, which began in an event whose precise nature we cannot access, will end in conditions we cannot fully predict. The darkness at the beginning and the darkness at the end are both in their own ways, beyond the current reach of science. We stand between them in the light, and we can see only so far in either direction. But here is what we do know. Here is what the physics says, with genuine confidence, independent of the uncertainties at the edges. The universe is evolving toward a state of lower and lower activity, higher and higher entropy, wider and wider separation between the structures that remain. The fires are burning down, not quickly, not on any timescale that should produce urgency or despair, but irreversibly. The arrows of thermodynamics do not reverse on cosmic scales. The stars will go out, the matter will decay, the black holes will evaporate, and whatever follows, whether it is a true and permanent heat death or a fluctuation back to order after inconceivable timescales, or the birthing of a new universe from the quantum ruins of the old, is further from the present moment than the present moment is from the Big Bang by a factor that defeats every attempt at analogy. And you are here, now, in the light. The question that remains the question that was implicit from the very first sentence of this journey, and that everything since has been building toward, is what that means. What it means to be a conscious observer in the one slim era of the universe's history, when nuclear fire burns in the sky. What it means that matter, over the course of 13.8 billion years of cosmic evolution, arranged itself into configurations capable of looking up, looking outward, and understanding, at least in outline, the arc of everything that exists. That question deserves its own answer, and it is the one we have left. You were born in the most luminous moment the universe will ever know. Not luminous in the way that word is used loosely as a compliment or a metaphor. Luminous in the precise physical sense. The universe at this moment in its history contains more actively burning stars, more ongoing nuclear fusion, more energy being converted from matter into light and heat per unit time than it will ever contain again. The peak of star formation has already passed. Cosmic noon was 10 billion years ago, but the era of stars is still ongoing, still radiant, still filling the observable universe with 1 trillion burning nuclear fires, and you are here for it. A conscious arrangement of atoms forged in the cores of earlier stars, standing on a planet warmed by a middle-aged yellow dwarf, looking up at a sky full of light that will not last. This is not a small thing. Consider what the journey from the beginning of this story to the end actually traces. It begins with the Stelliferous Era, the age of stars, a window of approximately 100 trillion years in which nuclear fusion burns across the cosmos, and the universe is warm enough, energetic, enough structured, enough for the kind of chemistry that produces complexity. Within that window, the Sun was born 4.6 billion years ago from a collapsing cloud of gas that itself was made from the expelled material of earlier stellar generations. Within the Sun's window of burning, the Earth formed and cooled and developed oceans and generated life. Within the window of life, multicellular organisms arose, and then animals, and then creatures with nervous systems complex enough to build internal models of the world around them. Within that window, a species emerged capable of language, of abstract reasoning, of mathematics, of science. And within the window of science, a few centuries long, a blink within a blink within a blink, that species developed the tools to measure the age of the universe, to trace the life cycle of stars, to calculate the rate of Hawking radiation, to predict with mathematical precision the sequence of events that will constitute the remainder of cosmic history. You exist at the end of that chain. You are the universe turned briefly towards self-examination. The atoms in your body have a history that stretches back almost to the beginning. The hydrogen in you, in the water, in your cells, in the organic molecules that make up your tissues, was forged in the first 3 minutes after the Big Bang, in a process called Big Bang nucleosynthesis, when the universe was hot and dense, enough for protons and neutrons to fuse. That hydrogen is nearly 13.8 billion years old. The carbon, the oxygen, the nitrogen, the calcium, the iron, every element heavier than lithium, was synthesized in the nuclear furnaces of stars that lived and died before the sun existed. When those stars ended, some gently shedding their outer layers into expanding nebulae, some violently in supernovae that briefly outshone their entire galaxies, they returned those elements to the interstellar medium. Those atoms drifted through space for millions of years before being gathered by gravity into the cloud that became the solar system. They assembled into the Earth. They dissolved into the ocean. They were incorporated into the first living cells. They were passed up through every generation of life that has ever existed on this planet. They are in you now. In a very literal sense, you are made of stars. Not poetically, not approximately. The atoms that constitute you were processed in stellar interiors under conditions of temperature and pressure that no laboratory on Earth can replicate. They were scattered across light years of space by stellar death. They were gathered by gravity and chemistry across billions of years into the configuration that currently thinks and breathes and wonders. You are not in the universe. You are the universe, temporarily organized into a form that can ask questions about itself. And the questions you can ask, it turns out, reach almost to the end. The arc traced in this journey from the warmth of the Stelliferous Era, through the cooling darkness of the Degenerate Era, through the silent patience of the Black Hole Era, through the evaporation of the last black holes and the arrival at heat death, that arc is not speculation, it is physics. The same physics that describes the fusion reaction happening in the sun's core right now also describes, in its thermodynamic and quantum mechanical extensions, the eventual evaporation of the last black hole 10 to the power of 100 years from now. The same conservation laws that keep the Earth in its orbit also dictate the eventual dissipation of every organized structure in the cosmos. The universe obeys rules. And those rules, followed honestly to their conclusions, tell a story with a shape, a beginning of extraordinary violence and heat, a long middle of burning and structure building and complexity, and an ending of cold and dark and stillness, so profound that the word ending seems inadequate. That is the story, and you have heard most of it. What does it mean? The instinctive response, the one that ambushes you when you truly absorb the scale of what comes after, is something like despair. If everything ends, if every star goes out, and every atom decays, and every black hole evaporates, and the universe arrives at a state of absolute entropic equilibrium from which nothing can ever emerge, then what is the point of any of it? What is the significance of a civilization, a species, a planet, single conscious moment, against a backdrop of 10 to the power of 100 years of subsequent darkness? But this question, as natural as it is, contains a hidden assumption. It assumes that significance requires permanence, that a thing only matters if it lasts, and that assumption examined carefully does not hold up. A piece of music does not become meaningless because it ends. A conversation does not become pointless because it finishes. A life does not become irrelevant because it is finite. The ending does not reach backward through time and cancel what came before. The light that existed, existed. The warmth that was felt, the understanding that was reached. None of that is undone by what follows. The universe over 13.8 billion years did something extraordinary. From a nearly uniform hot plasma of hydrogen and helium and dark matter, it built through gravity and nuclear physics and chemistry and time structures of staggering complexity and beauty. It built stars that fused hydrogen and synthesized the periodic table. It built galaxies that organized hundreds of billions of stars into elegant spirals. It built planetary systems. It built chemistry rich enough to produce self-replicating molecules. It built biology. It built nervous systems. It built consciousness. It built creatures capable of understanding, at least in outline, what they are made of and how they came to be. That is not nothing. That is perhaps the most remarkable thing that has ever happened as far as we know anywhere in the observable universe. Matter becoming aware of itself. The cosmos developing in at least one small corner the capacity for wonder. And wonder, it turns out, is not diminished by understanding its own impermanence. If anything, it is deepened by it. When you look up at the night sky and see the stars, those trillion burning fires distributed across a sphere 93 billion light-years in diameter, you are seeing a phenomenon that will not exist forever. The red dwarf stars that will outlast the sun by factors of thousands are still finite. The photons crossing the light-years between those stars and your retinas are being produced by fusion reactions that are consuming a finite fuel supply. Every point of light in the sky is a countdown. Not a countdown that should produce fear or grief, but one that should produce something closer to attention, to presence, to the particular quality of awareness that arises when you understand that a beautiful thing is temporary. The Stelliferous Era is approximately 0.014% complete. The fire has barely started by cosmic standards. The red dwarfs will burn for another 100 trillion years. The universe will be lit, however, dimly for timescales that make the present age seem like a prelude. But the direction is set. The entropy is increasing. The fuel is finite. And somewhere in the incomprehensible depths of future time, the last light will go out. What you have, what every conscious being in this era has, is the light while it lasts. There is a concept in physics called the anthropic principle, which in its simplest form simply notes that any observer capable of asking questions about the universe must, by definition, exist in a universe that permits observers. This is not as trivial as it sounds. The conditions required for the existence of conscious observers are extremely specific. You need stars that burn long enough and stably enough to allow planetary systems to form and stabilize. You need supernovae to synthesize and distribute heavy elements. You need a planet in a habitable zone with liquid water and a magnetic field, and a large stabilizing moon and a gas giant in the outer system deflecting some of the incoming asteroid traffic. You need billions of years of relative stability for evolution to produce complexity. You need the precise values of the fundamental constants, the strength of gravity, the charge of the electron, the mass of the proton to fall within the narrow range that allows atoms and molecules and stars to exist. The probability that all of these conditions are met simultaneously in any given region of any given universe is extraordinarily small. Whether they are met because of selection effects in a multiverse, or because of some deeper principle we have not yet understood, or simply because we are extraordinarily lucky, is a question that remains open. But the fact is that they are met here now, in this one unremarkable corner of one average galaxy among 2 trillion others. The conditions for consciousness are met, and consciousness arose. And through it, the universe has developed the capacity to know something about itself. That capacity, the capacity for a physical system to understand the physical laws that govern it, may be the most improbable and the most profound development in the entire 13.8 billion year history of the cosmos. More improbable than the formation of the first stars. More profound than the synthesis of the first carbon atom in a stellar core. because stars do not know they are stars. Galaxies do not know they are galaxies. The universe, for almost all of its history, has been a collection of physical processes unfolding according to fixed laws, with no part of it capable of representing those laws to itself, of asking what the laws mean, or where they came from, or where they lead. And then, in one small corner, in a brief window of cosmic time, matter arranged itself into something that could. You are that arrangement. Reading this following the argument, holding in your mind simultaneously the warmth of the present era and the cold of the distant future, the 100 trillion years of the Stelliferous Era and the Google years of the black hole era, uncertainty of what lies beyond heat death, and the certainty that you exist now in the light. You are the universe doing something it does almost nowhere, in almost no era of its history. You are the universe knowing itself. That is not an accident to be dismissed. It is not a coincidence to be explained away. It is the most remarkable fact about the current state of the cosmos, and it is a fact that will not persist indefinitely. The conditions that produced consciousness, the warmth of stars, the chemistry of carbon, the stability of planetary surfaces, the flow of energy from hot to cold that drives all biological processes, are products of the Stelliferous Era. When the era ends, those conditions end with it. Whether consciousness of any kind persists beyond the last stars in some form we cannot currently imagine is a question that science cannot yet answer. What it can say is that the conditions for the kind of consciousness we know require what the universe currently provides, which means that the light matters, not abstractly, not philosophically in some detached sense, physically. The photons reaching your eyes right now, the warmth your skin registers from the sun, the energy flowing through every living cell in your body. These are the products of a nuclear fire that will eventually go out, and they are the conditions under which awareness is possible. Every moment of consciousness that has ever occurred on this planet has been powered by the sun. Every thought, every experience, every act of understanding, including the understanding you are currently engaged in tracing the future of the universe to its conclusion, is running on stellar energy, on borrowed light, on the temporary surplus of a fire that will eventually exhaust its fuel. There is a temptation when you understand all of this to feel very small, to look at the scale of what follows the quadrillions and Googles and inconceivable Poincaré recurrence timescales and feel that the human moment is negligible, a rounding error in cosmic arithmetic, a candle flame in a room the size of the observable universe. But smallness is not the same as insignificance. A candle flame is not made less real by the size of the darkness around it. It is made more vivid, more present, more worth attending to. The darkness does not diminish the candle, it defines it. The universe will eventually be dark for so long that the entire Stelliferous Era, 100 trillion years of burning stars, will be relative to what follows as brief as a camera flash. The warmth that currently fills this corner of the cosmos will be in the arithmetic of deep time, an almost immeasurably small event, a fluctuation, a brief departure from the cold equilibrium that is the universe's eventual destiny. And in the middle of that fluctuation, on a small rocky planet, orbiting an unremarkable star in the outer arm of a spiral galaxy among 2 trillion others, matter became conscious. It looked up, it measured, it understood at least partially what it was part of and where it was going. It felt wonder. That wonder is not a small thing. It may be the most interesting thing the universe has ever done. The last red dwarf will burn for another 100 trillion years. The last white dwarf will cool for quadrillions of years beyond that. The last black hole will evaporate somewhere near the Google year mark, releasing its final Hawking photons into a dark and nearly empty cosmos. What follows is either the permanent silence of heat death, or the unimaginable patience of Poincaré fluctuations, or the rebirth of something new from the quantum ruins of the old. The physics points forward into uncertainty. The equations reach their limits. The story continues into territory that no theory currently covers completely. But here now the fire burns. 1 trillion stars. Right now, across the observable universe, 1 trillion nuclear furnaces are converting matter into light flooding space, with photons maintaining the energy differentials that make chemistry and biology and thought possible. The sun, your sun, is among them, one unremarkable yellow dwarf among a trillion pouring 8 minutes worth of light onto this planet, every second warming the oceans, driving the winds, powering the photosynthesis that built every forest that ever existed. You are warmed by it right now. Whether you can feel it or not, the sun's light is reaching you directly or indirectly, as it has reached every living thing that has ever existed on this world. You are part of the chain that began with hydrogen in the Big Bang and passed through stellar nucleosynthesis and planetary formation and 4 billion years of biological evolution and arrived finally here, at this moment. At this understanding, the warmth is not permanent. Nothing in the cosmos is permanent. The physics is clear on that point, and the physics does not negotiate. But permanence was never the measure of value. Presence is. Attention is. The capacity to look at a universe that will eventually go dark and say clearly and without flinching, I see what this is. I know what it costs. I am here for it. The stars are burning now. Every second the sun converts 600 million tons of hydrogen into helium and light. Every second that light crosses 93 million miles of space and reaches this small, improbable, temporary, extraordinary world. Every second the fire that makes consciousness possible continues to burn as it has burned for 4.6 billion years, as it will continue to burn for approximately 5 billion more. The darkness is coming. It is coming on a timescale so vast that it touches nothing in any human life, any human civilization, any span of time that human language has ever needed to describe. But it is coming. The physics is patient. The entropy is increasing. The fuel is finite. And the universe which began in fire and will end in cold is currently somewhere in the middle of its one luminous era, burning through the hydrogen. It was given at the beginning, making light while it can. You are here for it. You are here right now in the warmth, in the entire future of the universe, the quadrillions of years of cooling white dwarfs, the Google years of evaporating black holes, the incomprehensible expanses of the dark era, stretching beyond all reckoning. There will be no moment quite like this one. No moment in which the fires burn at this density, in which the temperature gradients are this rich, in which the conditions for complexity and consciousness are this generously met. The Stelliferous Era is the universe at its most alive, and you are in it. Not at its peak cosmic noon was 10 billion years ago, but in it, in the light, in the warmth, on a planet that is spinning and orbiting and carrying you through a galaxy that is itself turning through a cosmos that is still for now full of fire. Look up on a clear night, and you are looking at 100 billion stars in the Milky Way alone, each one burning, each one consuming its fuel, each one measuring out its finite store of hydrogen against the immensity of time. The sky is not a backdrop. It is the evidence. It is the universe showing you what it is doing. With the energy it was given at the beginning, it is making light. It is making warmth. It is making in at least one place the conditions under which matter can understand what it is made of. The last light is a long way away, longer than any number you have ever needed before, longer than any analogy can bridge, but it is coming. The physics is honest about that. And the honesty of it, the clarity of the picture, the precision of the trajectory from here to there, the fact that human minds working with mathematics and telescopes and particle detectors have been able to trace the full arc of cosmic history from the Big Bang to the evaporation of the last black hole, that honesty is itself something extraordinary, something worth sitting with. The universe will go dark. But right now, for this brief, radiant, improbable moment in the middle of its one luminous era, it is burning, and the light is here. On this world, in this moment, in the warmth of a star that has been burning for 4.6 billion years and will burn for 5 billion more, the light is here. It is extraordinary. It is temporary, and it is ours.